slides and hear me well?
Yes, we can see it. Thank you.
Great. So it's really a pleasure to talk to you here at this anniversary meeting, and thanks a lot to the organizing committee for having invited me. It's really an honor to present here some of our latest work in this field of environmental impact. And just to start with this topic, I like very much this graph. This is from a document that is called Planetary Health Check that came out last year. And this shows very nicely the climate history of Homo sapiens, where you see different phases. So the first is the Pleistocene, it's the Ice Age, basically. And what you see here is in terms of temperature, that it was colder, of course, because, I mean, that's why we call it the Ice Age. But there were quite important temperature variation from time to time. And in this phase, humans were basically migrating all the time because the climate was not stable. And then, and this is the second panel, there was a change in the climate due to orbital, for example, orbital aspects of the Earth around the sun and other things. So nothing anthropogenic. And then the climate stabilized at the temperature level that we knew basically still at the time when I was born. And this is shown here as the green, as like a green corridor. And this stability, in fact, allowed humans to settle down. The period is now the Holocene. And this is basically the basis why humanity could found civilizations. And now in the last panel, you see what's going on over the last few hundred years, that we are gradually moving out of this green corridor, here shown at least for the temperatures, that you see that we have already a temperature increase of about 1.1, 1.2 degree for the global temperature. And the question is, of course, I mean, what does this mean? And what does this mean is that when scientists looked into what you need basically to stabilize the Earth system, and they found basically 9 different areas that you need to watch for to stabilize the Earth system. And they've also found that in 6 out of 9 of these areas, we are already moving out of the stable region. And this is what is called the planetary boundary framework. I mean, you know, of course, talk a lot about climate change, but you see even here, I mean, it's in red, but I mean, when you see basically the size of it, there are even bigger concerns like biosphere integrity. That's basically the 6th mass extinction in which we are in. Novel entities, this means basically everything that doesn't exist naturally on Earth, like plastics or genetically modified livings, but also other things like geochemical flows. This is basically nitrogen and also phosphorus flowing in the ocean and creating dead zones, or the use of the land system. It's basically deforestation. We use much too much land for feeding animals, for example, and also freshwater change. You all know we have increasing stress on the freshwater supply and so on. So these are all issues of concern. And even if you, because some people say, okay, we just have to move to renewable energies and everything is fine. You eventually will fix climate change, but renewable energies will not fix novel entities, biosphere integrity, and so on. So you have to step back a bit and have a much more systemic approach. Now, why is science concerned about that? And when you, for example, read the IPCC reports, they clearly say that all human activity sectors need to reduce their environmental footprints, specifically for the IPCC, the carbon footprint. And this, of course, applies also to scientific research. First of all, I mean, I think really it's an ethical responsibility of scientists to do so. There was, in fact, a little bit more than 2 years ago, a report from an ethics committee in France, the CNS Ethics Committee, which clearly say that we have to integrate environmental implications into the conduct of research as an ethical responsibility. It's like doing experiments with animals or even with embryos. It's at the same level. We have to be concerned about our environmental impact. And then, in fact, what people don't know so much, there are even institutional obligations. For example, the European Space Agency, and I will talk a lot about space in this talk, they have an obligation to reduce the carbon footprint by 46% over the next 11 years. This was a council resolution adopted at the council meeting. And then I have two examples in France, but I guess the similar examples exist elsewhere. For example, for higher education and research, we have an obligation to reduce by 5% each year the carbon footprint. Even for our labs, recently a letter was sent at 6%. And then, for example, you have a French national carbon strategic plan. And also here there are targets for emission reductions. So it's really also an obligation to reduce the emissions. Now, what do we know specifically about the carbon footprint? And I show you again here some examples that I know very well, because they are from my lab or for France, but very similar numbers come out in other countries. So on the left, you see a carbon footprint assessment that we did for the year 2019 for our lab. And the thing that was new there was that we tried to be as exhaustive as possible, including really everything what needs to be included in a carbon footprint assessment. And what was coming out from this study was that the per capita, and for example, just to mean what capita means, just everybody working in the lab. And in our lab, it's, for example, half researchers and half technical staff and administrative staff. So if you wanted to have it per astronomer, you would have to double this number. So per capita, we have a footprint in 2019 of 28 tons CO2 equivalent. And what was new in the study was that we found out that 55% of this footprint comes from the use of astronomical facilities, ground-based observatories, space observatories. And very similar study was done recently for France globally, looking at all labs in France. And the finding is very similar. So they found 20 tons per capita for France globally, and there 62% of the footprint coming from the astronomical facilities. Now, Sarah mentioned already Labo 1.5, and I wanted to also introduce this quickly to you for those who don't know this. It started a bit like Astro for Planet Earth as a grassroots initiatives from just researchers globally, not only in astronomy, but globally in France, that wanted to better understand the environmental impacts of our research activities. And now, in fact, it's two things. It's first an official research group recognized by CNRS and even funded by CNRS. And then, in addition, it's still a kind of grassroots initiative with seminars, reflections, arts and science, and so on. And they developed a number of tools. And for example, one very impressive is a carbon footprint estimation tool so that all labs can estimate their carbon footprints. And the interesting thing here is that, I mean, if you have one tool and everybody uses it, you can do research, you can make comparisons and so on. And just you see the numbers here, there are now basically 3,000 carbon footprint estimates for labs in this tool, and made by a little bit more than 1,400 labs. So this means a number of labs have done now several carbon footprint assessments to also study the evolution. And there are other tools to get in action, to model scenarios for footprint reduction. And of course, also tools to get connected between the labs to learn from each other. And just to illustrate what you can do with these tools, this shows you how the situation moves on at IRAP. So this is not exactly the same numbers that I've shown you before, because the tool uses a bit of different methodology compared to what we used before. And this shows over 3 years how the carbon footprint evolved. There's a gap here, 2020, 2021. We haven't done any estimate because of COVID. So we have a pre-COVID estimate and 2 post-COVID estimates. And you see the different contributions. So one takeaway is that there are fluctuations. And that's normal because, for example, in purchases, we don't buy every year the same amount of stuff. We do a lot of instrument development. And if there's a year where there's a lot of instrument development or a new big mission coming in that is developed, then we have a higher purchase footprint compared to other years where maybe the investments are lower. And the same is true for what is called here research activities. That's the use of observatory data. It's obvious that this fluctuates a lot because here the attribution depends on the number of publications done by researchers in the lab. And since this is also fluctuating, it's very difficult to get something, I mean, really in terms of trend out of this. So this is maybe not so much the interesting part. The interesting part is that when you look at our travel footprint, you see that consistently from 2019, it went down by a factor 2, basically. And discussing with other labs in France, at least, that's also observed there. So this seems to be a global trend. I believe it has two factors, of course. Of course, one is it's post-COVID. And during COVID, we all learned that we can, like now, today, make video conferences. So we don't have to always meet in person. And second, certainly also that people are more and more concerned about environmental impacts. And deliberately, people move away from air traveling, go to plane traveling, or just no traveling. So this is, I think, the good news that, I mean, things are really moving in this sector, in the travel sector, at least what I see in our lab and in other labs in France. And I hope things are similar also in other countries, but I don't have any data on that. Now, going a step further, so I talked a lot about carbon footprint. So what do we know about other environmental footprints? And there is, in fact, a standardized method to assess other environmental footprints, or even all environmental footprints. And this is called life cycle assessment. There's an ISO standard, there are many other standards, and there are even entire journals about life cycle assessment. So the basic idea is the following. Take, for example, a satellite like you see here, and you go through the entire life cycle of the satellite through design, qualification, launch of the satellite, use of the satellite, and at the end, eventually disposal. And you look for all phases, basically what flows into the satellite from nature. So natural resources, energy consumption, and so on. And what flows out into nature, like emissions in air, water, soil, and also waste. And from that, you get a lot of impacts like the depletion of fossil and mineral resources, but also global warming, ecotoxicity, ozone depletion, whatever you want. So you can study a lot of these indicators. So over the last years, we basically learned how to use this method. You need also tools and some investment to get these tools to make these assessments. And you basically made two different assessments. So one was for a ground-based telescope. This is, and here's a picture of it, just to give you an idea. So this is for Cherenkov astronomy, so gamma ray astronomy, very high energies. The telescope is typically 460 tons of foundation. You see this concrete foundation at the base. And then you have 82 tons of telescope structure, including the mirrors and so on. And at the end, this white box is a camera, and this camera is quite big, weighs 2.1 tons. And we looked into the footprint of construction and operations over 30 years. And then the second project to which we looked into is a space instrument. So here it's only the instrument. We are not making the entire satellite. We are just building an instrument in a collaboration for the Athena X-ray mission, a European Space Agency mission. And just to give you an idea, I mean, here the object is much smaller, only 220 kilograms. And we only looked into the development of this object and its construction up to the point where it's delivered to ESA for integration in the satellite. So no operations and so on, no launch of the satellite, just the object itself. Now, what you get out of this is a graph like that. So this is for the ground-based telescope. So what you see here on the y-axis, these are all the different environmental impacts that we looked into. I mean, this is according, again, as a standardized methodology. The one that is recommended here from the European Commission has 16 different impact categories. For example, global warming means basically CO2 equivalent emissions, but you have other things like ozone depletion, particulate matter, and so on. Now the x-axis, this is just a number here, and the unit is points. And 1 point is basically the average environmental load of a human on Earth. And the reason why I express it here in points is because then you can compare things directly. There's of course some judgment behind how do you compare global warming to, for example, mineral resource depletion. So how do you weight basically these two different things? But nevertheless, I mean, since there's a standard, you can use it and make things comparable. And that's what's behind this score. So you can add up basically the different bars to get a single score, which is indicated here, is almost 300 points. So the environmental impact of construction and operation of this telescope is something like 300 humans per year. You see now the big impacts, for example, are global warming, and I just put the number here. It's 2,660 tons CO2 equivalent. And interesting now, here we can learn where it comes from. So the global warming comes from the construction of the telescope. And this is because of the steel. Use of steel is quite impacting, and specifically the transformation of the steel. So you have machining, but what is very impacting, for example, here is casting. Steel casting has a very high impact, we found out, and that's why this blue part is so important. Then you see a big red part, and this is the power consumption. Once the telescope is on site, and that's so big here because we are operating in La Palma, and La Palma has a very high carbon intensity for the energy generation. But very interesting, a very high environmental impact is also mineral resource depletion. And here you see it also comes from the construction of the telescope because it's a big thing, and also again the steel production, the aluminum and so on. But then you have a very big green bar, and that's the camera. That's the construction of the camera. And this you always get if you have an object where a lot of electronics are involved. It boils down to using elements like gold, for example, in the electronics that create these high impacts. And that's found also in other studies, and seems to be really a kind of general pattern. So we really have to worry at the first place about the global warming, but also about the use of resources. Interesting, for the space instrument globally, it looks similar. Global warming and use of resources are the prime impacts. What's very interesting here, you see the object is much smaller, only 200 kilograms, but the impact is a factor of 10 higher. The single score is over 4,000 points and over 25 kilotons of CO2 equivalent. And now where does it come from? So for example, the purple, this is the AIT, the assembly, integration, and test activities for the object. And behind that, it's in fact the clean rooms. The clean rooms that you need to make these activities, they consume a lot of energy. You have to generate a stable environment locally in these clean rooms. And this is very impactful. And that's also coming out of other studies. The clean rooms are really a big issue for space sciences. Then you have the green thing is office work. It's just you need a lot of people working on these instruments. They all need power in their office, heating, climate, air conditioning, and eventually a computer, laptops, and so on. And just all this manpower basically has a very important environmental impact. And then at the end, and we all know this, traveling, of course, you have to have there's a lot of traveling involved with project meetings and so on. So these are the big impacts specifically for global warming. So it's not so much the object itself, it's really all the activities around it. And when you come to the object itself, this is mineral resource depletion. You see it shows up different models, pre-flight models in blue and the flight model in green. Again, it's use of electronics in the instrument that create a lot of the impact here. Okay, from that, the interesting question is where do we move? These were all not snapshots. So one of the studies we did recently was to look in the temporal evolution of our infrastructures. And this shows you on the graph here the number of operating facilities over the years, basically from World War II on. So, for example, when you look at the end of the graph, you see today we have over 400, I think 30 operating facilities. And of course, they are dominated by facilities on ground, optical infrared telescopes, these are OIR. Of course, there are more small telescopes than big telescopes. And then you have radio telescopes or radio arrays. And for space, this is basically by major theme: astrophysics, planetary sciences, plasma physics, solar physics. These are all these bluish, purplish colors on this graph. So you see there was a huge explosion of this number of facilities over the years. And now we use this huge database that is behind it to estimate the carbon footprint evolution over the times. And that's what you get. So the first thing is that you see blue all over the place. So really the space part is the dominant part of our facilities. So satellites, probes, and so on. Second point here, the y-axis has two different scales on here, because there was a big peak in the 60s, beginning of 70s, related to the space race and the exploration of Moon, Mars, Venus, and so on. And there the annual carbon footprint skyrocketed to 12 megatons, basically. But then, of course, decreased over the time once the space race was all over, basically. What you also see then, there's quite some noise here, fluctuations in this graph. And that's because of what weights in is basically the building of big, huge facilities like the Hubble Space Telescope, the Gamma Ray Observatory. And when you build these big telescopes, they really show up as individual peaks in this curve. What is worrisome that there seems to be now even bigger peak over the year, more recent years, the last decade or so. And when you look in detail, you find out that behind that is a new space race, a lot of new missions to the moon coming up, but also to other planets like Mars in particular. So what we did, we tried to look into the future. And here basically we did some kind of extrapolation to estimate, okay, what will happen in the next years, and we went even to the end of this century, depending on the actions we take. And what you have here is basically always two curves. The solid line is always a trend based over the past 45 years. So we excluded basically the first space race because this was really very particular. And then we progressively shrinked the period over which we estimated the trend to 30 years to estimate somehow what is the uncertainty related to the period we use for estimation of this trend. And then you see, for example, in this case, if we don't change anything in our way how we do research as usual, you eventually have a flat curve, or it goes up. So why the curve is flat? There's one thing behind all this study is that we also take into account the decarbonization of the industry as observed. It's observed over the last decades that the industry is really decarbonizing as a typical rate of 1.4% per year. Very steady rate, in fact, it's really impressive. And we just assume that it will also continue like that. So there's decarbonization folded in this graph. And then the solid lines is where we should be in terms of the Paris Agreement. There are two lines, one for 1.5 degree and one for 2 degrees. Okay, so you see we don't match the Paris Agreement. So what can we do? Okay, we can increase decarbonization. We can say we double the decarbonization rate. We move from 1.4% to 3%. This is quite ambitious already because it means really a lot of investment to make this. Then the carbon footprint goes down, but it just goes down too slowly. We're still much above the Paris Agreement trajectory. So that will not help us to really fix climate change. Another alternative, a bit more disruptive, is that you could say, okay, we have a lot of facilities now, just let's stop there, don't build more. This doesn't mean that you don't build any facility anymore. It just means if some facility comes out of service, you just replace it by a new facility of equal amount. So you freeze the number of facilities. So there's still something going on, but somehow slower in some way. And you just keep with the same level that we have today. And when you do that, it's like basically doubling decarbonization. It's doing the same kind of job. It's reducing the carbon footprint, but not fast enough. So you can say, okay, let's add these two together, freeze the number of observatories, and make a deep decarbonization. It's getting better, but it's still not yet there where we should be. And if you just look in what we need to do to come to the Paris Agreement trajectories, this means we would actually have to reduce the number of operating astronomical facilities by something like 3% per year, and in addition, double the decarbonization. So what can we take away of all that? So how can we make our field really sustainable? So the first thing I tried to convince you is here that we really, I mean, to make the field sustainable, we need a degrowth in the number of operating facilities. There's just no way to keep on as we are going, specifically, as you have seen, we are in a growth situation, specifically with new missions going to the moon and so on. There's just no way to make the field sustainable with such a growing situation. If you look to other things than facilities, it's of course the purchases need to be reduced. You see, purchases are a very important contributor to our carbon footprint specifically, but this will probably also hold for resource use and so on. Well, professional air traveling needs to decrease. We all know that. And actually the good news is it's going in the right direction. Also, what's not so much on the radar is the home to office commuting. It just needs to be decarbonized. I mean, you can of course think about electric cars, but also you can think about public transport, cycling, walking, and so on. I mean, for our lab, where we have, for example, electricity is not very carbonized, it shows up as some contribution to our basically global footprint. And then, of course, the energy consumption of office building need to be reduced and decarbonized. For example, you've seen the very important impact of clean rooms for space sciences. So if you can reduce that part, you will reduce probably also the clean room impact and the impact also of human resources on space sciences. So what this actually means for our field is that our research practices need to change. And I think there are different ways how to do it. For example, moving more towards collaboration instead of competition, because we know in terms of instruments, for example, we often do the same instrument several times because every country or region wants to have their own biggest telescope of the world. Europe is doing the ELT, the Americans want to have the TMT or the GMT. The Chinese also certainly will come up with something. But scientifically, in fact, one instrument of this size is sufficient. And of course, in the space field, this also exists. When you just look at the number of missions sent to Mars, or in the next years going to Venus, I mean, if we just would send one mission to these planets, isn't this enough? So there's maybe an area for improvements. Another thing is also just using data that is already existing, archival data. There are a lot of them out there. That's, for example, something I personally develop, and it's really very satisfying to do that. And just you don't need these new telescopes to do your research. And then we need more investment in decarbonization and less, in fact, in new facilities. which is just needed if you want, for example, to double the decarbonization as indicated in these scenarios. And in fact, a very interesting metric that could be used, of course, it's difficult to quantify science output, but if you think a bit like that, how can I basically maximize the science output per money spent? Of course, you can do for the same money more science, or you can do the same science with less money. But at the end, it's a bit like that. I mean, if you can think about that, I think it will automatically also reduce the environmental impacts of our research. And I think I leave it here. I think the important thing is that we need to engage in a debate about these things, how we can change our research practices. Calling for online meetings is, of course, great, but by far it will not be enough. Okay, that's it. Thank you.
All right. Thank you very much, Jürgen. Very cool. And definitely a great introduction and pointer towards the breakout sessions later on. So I'm sure there's a lot we can discuss about this. Certainly we can't cover everything today. And yeah, thank you for this nice presentation about all these insights. And as it often is with scientists, the focus is there is some focus on the great things you did, but one of the questions that did, of course, come up is why did you not do this and this? And there's even more you could do. So, particularly regarding the launch of this instrument. So, for a full life cycle assessment, could that be included, or could you comment on what an estimate for the launch could be? So, yeah.
Yeah, I mean, in fact, I have a parallel activity. I looked a lot in the global impacts of space, the space sector, basically globally, including launch and so on. And I'm very solicited by the French Space Agency and by even other agencies to talk about that. So to give you an idea, just a rough estimate. So for a complete mission, half of the impact comes from the launcher and half of the impact from the satellite. It depends, of course, on the size of the satellite. If you launch something like the James Webb Space Telescope, most of the impact will come from the telescope and not the launcher. And the same if you launch a little CubeSat, it's certainly also not that way. But just to give you a rough idea. Now, there's one caveat to that in fact, we have no clue what's going on in the higher atmosphere, in the stratosphere. It's just a knowledge gap. We know that, I mean, launches are the only human activity that injects stuff in all layers of the atmosphere. And we know that depending on what fuel you use, for example, you use a Falcon 9, it burns kerosene. This will inject a lot of what is called black carbon in the stratosphere. What black carbon does is it stays up there for some time, and specifically we don't know how long it stays up there, but we know it stays up there for some time. It makes us green. So interesting, it eventually may even cool down the troposphere because less light will come to the troposphere, to the Earth's surface, but it will heat up the stratosphere because the carbon, the particles are heated up. It will destroy the ozone layer. So in fact, the biggest issue there is really the destruction of the ozone layer by space launches. And eventually, I mean, it will change whatever rain patterns on Earth and so on. It's a bit like geoengineering when you launch a rocket.
Okay.
And the same is true for alumina. So if you have the boosters of the Ariane, for example, you burn aluminum in them, the same process. The aluminum destroys chemically the ozone. So ozone destruction is a big issue. And there are estimates that the impact also in terms of CO2 or global warming could be much higher from rockets than what is currently known. So that they could eventually completely wipe out. I mean, I could speak hours about it. So I think I stop here. They could wipe out all the rest.
Yes, yeah, more discussions to come. So two more questions were regarding the average carbon footprint, I think, of a human. And for that, maybe I would point to a different paper and works from other A4 years where we compare the average carbon footprint of an individual astronomer. So maybe we can put that in the chat later. And there's also been a question about computing. And I think also for that, there's some publications out there that we can share, just in the interest of time, sorry. And then there was one more question about the materials used. So I think it was about slide 12, where you showed where this information about the construction and everything, but is there also information on how these materials were sourced and if there's any human exploitation involved in that?
Oh yeah, I mean, many interesting questions indeed. So you have to take a bit care when you compare, for example, these 28 tons per capita to what you often hear we have to be at 2 tons per capita globally in 2015 and so on, because these estimates are not made the same way. I mean, when you make the estimates, a carbon footprint estimate, you basically look what's your global footprint in the sense that what actions can you do to reduce this global footprint. But when you think about it, there's of course some double counting, because the company that will build, for example, the rocket or whatever, also has a carbon footprint. It also accounts for the rocket somehow in this footprint. So you have to take a bit care about the double counting, and it's not so tricky to make a comparison of absolute numbers. That's why I think it's more, in fact, interesting to look at trends and see the evolution, look at relative evolutions. I think this is more pertinent there. There were so many questions. I mean, I just remember the last one about the eventually how you extract the resources. That's not taken into account. I mean, when you make these life cycle assessments, all the environmental impacts are taken into account. So there's all the mining activities behind, of course. But we have to be aware, I mean, where the stuff comes from and who actually gets out the stuff from Earth. And there's a lot of child labor involved with that when you think about cobalt in Africa and other things. I mean, we really have to get the material footprint down. And so just moving everything to batteries and electrical just will create a big issue there if we can go on it that way.
Okay. All right. I think in the interest of time, we'll have to move on now. There's more questions in the chat, so Jürgen, please feel free to follow up and answer them if possible. But we'll also make sure to try to convey them to the breakout sessions, because there's definitely a lot more nice discussion to be had. So after this, we'll have a short little break, and to transition back from the break, I'll play another video later, and Leo will take on after that. So before I let you go into a little break and then hand it over, I want to thank again the organizers of this meeting. So I had the pleasure to introduce you here, but the workload of most of the meeting has been with Imani Ware, first and foremost, and several other organizers. So maybe they can wave or give a little sign, raise their hand if you've been in any meeting for the organization of this meeting. Maybe you can raise your hand so that we can all give you a little applause and appreciation. It's been really great for setting this up. Yes. Some people I see they are not necessarily raising their hand yet, but yeah, I just wanted to thank you all again. And with that, I'll let you go into the break of about 5 minutes. And once the video is done, Leo will take over. So thank you very much for tuning in, and talk to you in a little bit.